Let us look at using integration to calculate areas. What I have here is the curve y equals x squared. I have below the curve and to the right of it, it's shaded red, and above the curve and to the left, it's shaded blue. We want to calculate the area that is below and to the right of the curve. Now, let us first of all find the total area here. This is our rectangle. The height is 4 and the width is 2. So we can see that the area of the rectangle, let's just do this, the area of the rectangle is equal to 2 times 4, which is 8 square units. All right. Now, we want to calculate the area in red. Remember now, in doing so, what we're doing is cutting up this area. Oh, no. We're cutting this area into rectangles, although these wouldn't be strictly rectangles. They're really trapeziums. You could approximate them to being a trapezium. Each of them would have a curve at the top, like this, and then you go straight down. All right. Now, what we're saying then is we're finding the sum of, now here, the height. Consider the height of these. You could consider the maximum height, or you can consider the lower height here, or the average height, whatever the case is. The height times the width of each rectangle. So the area of each rectangle is height times width. But the height is what? If this is x, the height is x squared. So we're summing up x squared times the width. Now we have x here. Call this x0, x1, x2, x3, and so on. Where each of these is the point where they would have started, x2, x3, and so on and so forth. All right? Now, the height times the width. x1 minus x0 is the same thing as x2 minus x1, and so on, because they are of equal width. Let's call the width a change in x. Call it delta x. Delta x. Now we're summing up from 0 to 2 of x squared delta x. You see that? We have all these rectangles. The height is x squared. The width is delta x. So the area is height times width, x squared times delta x. Now, as we make more and more rectangles, the change in x, the delta x, gets smaller and smaller. Now, What we finding out here is the limit as delta x tends to 0. If we imagine the number of rectangles getting larger and larger and larger, then the width getting smaller and smaller and smaller. As the number of rectangles approaches infinity, the width approaches 0. So the limit, as you sum from 0 to 2 of x squared delta x, is equal to, the symbol I use now is this, the integral sign from 0 to 2 of x squared dx. Alright. So now we have a definite integral where we define the boundaries. The lower boundary is 0. The upper boundary is 2. So let us perform the integration. Since we're using the red area, let's perform it in red. The red area is equal to the integral from 0 to 2 of x squared dx. So we're integrating with respect to x. That is equal to x to the 3 divided by 3 from 0 to 2. Alright? Now, this would be 2 to the power of 3 divided by 3. When you substitute the upper boundary for x minus the lower boundary now, 0 to the power of 3 divided by 3. So, this would be 8 thirds. So the area of the red part is 8 thirds. So let's say the area of this part is equal to 8 thirds. Now that you see this, what's the area of the blue part? Well, what you could do, since the total area here is that of a rectangle of 8 square units, you could say the area of the blue section, the part that looks like this, is equal to is 8 minus 8 thirds. 8 square units for the rectangle minus 8 thirds. It would be 8 thirds for the red area. So this is equal to, let us see now, how do we deal with this? This is 8 over 1, you know. So if we use common denominators, 3 8 24 divided by 313, we multiply both the 8 and the 1 by 3, so that we minus 8 thirds. So now, if we have 24 thirds and minus 8 thirds, what do we get? 24 minus 8 is 16, so it's 16 thirds. But it's a blue area, so we write it in blue, 16 thirds. Unit square. Oh, by the way, I didn't put the unit square here. No, it's 16 thirds. Let us look again at another method of calculating the blue area. Let's do some erasing over here. Right. We want to calculate the blue area now. Here, what we can do is divide up horizontally, so you divide the y axis into rectangles. Alright? So if we do that, what we have as the height of the rectangles. Let's call them, let's say this is y0, y1, and so on. So this is the height. y1 minus y0 equal, instead of delta x now, since it's on the y-axis, it's delta y. Alright? So this is delta y. Now, the width of the rectangle, each rectangle, what is it? Would it go along x? We started with the formula y equals x squared. Suppose you write this as x equal, what would it be? If you transpose for x, you get x is equal to the square root of y. Well, it's plus or minus square root of y, but since it's here, we're interested in just the positive values. Now, the x, the width, is changing. It is the square root of y. You see that? Those are the width of each of them from 0. Now, suppose you consider doing this now. You have the sum, let me write it over here. The sum, let me write it, from 0 to, now the fact is, when you had x equal 2, it goes up to 4 because 2 squared is 4. So you're summing from 0 to 4 of, now what is it that you're summing up? It's the square root of y, because remember, here, the width is the square root of y, whatever y is. This width is the square root of y. For example, when you reach up to 4, you go across and go down, you get 2. Alright? And so on. You could check it out with this graph. So, is the width times the height of each rectangle, which is delta y. You see that? Each rectangle is square root of y wide by delta y high. Alright? Now, what is the limit? As you increase the number of rectangles here, you cut it up into more and more rectangles so that the height of the rectangles gets smaller and smaller and smaller. What you will have is that the number of rectangles approach infinity while the height of each rectangle approaches 0, right? So, the limit as you sum from 0 to 4 of the square root of y, delta y, is equal to the integral from 0 to 4 of the square root of y dy. Now, let us carry out this integration. Remember, we want to see if we get 16 over 3. And since this is the blue area, let us write it in blue. So we find the integral from 0 to 4 of the square root of y dy. But what's the square root of y? Or what's another way we can write it so we can differentiate, integrate it? It's y to the power of a half. You have to remember that. square root of a number is the same as the number to the power of a half. Now, this is going to be equal to y to the, remember the power rule, half plus 1 divided by the new power, half plus 1. Your square brackets around it from 0 to 4. Now, this is equal to y to the, what is half plus 1? Half plus 1 over 1. We use our knowledge of fractions now. If you multiply both top and bottom by 2, we get 1 half plus 2 halves, which is 3 halves. So it's 3 halves, 3 over 2, divided by 3 halves. From 0 to 4. Equal. Alright. So, you put in your upper boundary now. Y is 4. So it's 4 to the 3 over 2, 3 halves, divided by 3 halves, minus 0 to the 3 halves, divided by 3 halves. Okay? You see that? Now, what will we get? This is, remember, when you have a number raised to a power that is a fraction, the numerator, the top number, gives the power that you raise the number to, and the bottom number, the denominator, is the root of the number. So this is the square root of 4 cube, or you could, if you want, write it as the square root of 4 cube. You'd have to cube 4 and then find the square root, but the cube of 4 is a big number. So find the square root of 4 first and cube it. You're dealing with smaller numbers. Good. Divided by 3 halves. Minus, well, 0 to the 3 halves is 0, and 0 divided by 3 halves is 0. So this is just 0, right? So what will happen here is the square root of 4 is 2. So we have 2 to the power of 3 divided by 3 halves. 2 to the 3 is 8 divided by 3 halves. But this is the same as 8 multiplied by, remember when you have a number divided by a fraction, it's the same as the number times the reciprocal of the fraction. So 8 to 16 over 3 units squared. Alright, what did we get up here? 16 over 3 units squared. So it is correct. So just review. We have the curve y equal x squared. We shade this side in red and this other side in blue. And we say that we want to calculate the area of the side that is in red. So it is really the integral from 0 to 2 of x squared dx. When we work that out, integrate it and put in the upper and lower boundaries, we get 8 over 3, 8/3. Then we say, suppose we want the blue area, the area that is to the left and above the curve. We could do it in two ways. Since we know the red area already, and we know that this is a rectangle of height 4 and width 2, 2 times 4 is 8. So you could say 8 minus 8/3, which we got for the red area, gives us 16/3 square units. Now, suppose you're asked to do it by integration. You have to consider that you divide up this area into rectangles. They would more look like trapeziums, but as you increase the number of rectangles, the number of trapeziums, right? You could approximate like the curve here as to a trapezium, but the idea now is that it's not accurate with a few trapeziums, not that accurate. So as you increase the number of trapeziums, the width of each increase. So what happens? You cut this into number of trapeziums. The height is the change in y, or delta y. That's the height of each trapezium. The width will be the square root of y when you transpose y equals x squared. So as you increase the number of trapeziums and the width increase, the limit I should put here as delta y approaches 0. Alright, the limit as delta y approaches 0, that means as the height of each approaches 0, because you're using more and more rectangles or trapeziums approaching infinity, the limit from 0 to 4 of square root of y the delta y is equal to the integral from 0 to 4 of square root of y dy. So we're going from 0 to 4, which means you're going up this way. Alright? Now, so what we do is carry out the integration. Square root of y is y to the half. Integrate it, you get y to the 3 halves divided by 3 halves. The boundaries are 0 to 4. You carry out the integration and you get the same thing, 16/3 square units for the blue area. Alright? So that was finding the area under a curve using integration. I'll see you in the next video.